Have you ever heard that empty space is nothing, like a perfectly still void? That idea collapses the moment you realize space can have different energy states, and those states can change the way water can freeze or boil. In the most extreme scenario, our entire universe could tunnel from a false vacuum to a true one in a single catastrophic transition. The consequence isn't slow. It's like a switch flipping across the cosmos. But here's the twist. The first bubble wouldn't be a bomb crater in space. It would be a new vacuum phase forming quantum mechanically, a sphere of lower energy that expands at nearly the speed of light. The open question is terrifyingly specific. How can a system get from a higher energy metastable state to a lower energy stable state without ever crossing the barrier smoothly? And what happens to the universe's entropy, the bookkeeping of disorder and available microstates when that happens? To understand false vacuum decay, we need the before state. Cosmology models the universe using quantum fields. Think of a field as something that exists everywhere in space, like a choir sound spread through a hall, except the choir is quantum, and the notes are energy levels. The simplest baseline is the vacuum, the lowest energy state the field can occupy. But lowest isn't guaranteed if the universe is trapped in a metastable configuration, a local minimum of the potential energy landscape. That's false vacuum. In particle physics, such situations appear in theories with symmetry breaking where multiple minima can exist. In the early universe, temperatures and fields could have left it sitting in a higher energy pocket. The prevailing view before detailed bubble nucleation calculations was that transitions would require thermal activation. The system heats up, crosses the barrier, and relaxes. But the early universe also had regions with effectively zero temperature relative to the barrier height, forcing a different mechanism, quantum tunneling, now the core mechanism. Imagine a mountain valley with walls you cannot climb over because you lack enough energy. Classical rules forbid crossing. Quantum rules allow something subtler. Even if you're trapped on one side, there's a non-zero probability that the field configuration momentarily appears on the other side in a way that satisfies the equations of motion in imaginary time. The cipher-optical picture describes this as nucleation. A rare fluctuation creates a critical bubble where the field sits near the true vacuum inside, while outside remains in the false vacuum. There's a critical size because smaller bubbles shrink away. Larger ones become energetically favored and grow. The bubble doesn't start from nothing at a point and instantly become macroscopic. It emerges from the path integral as the most likely tunneling history, often described by a bounce solution. In space-time, the bounce is like a curved world sheet separating false vacuum exterior from true vacuum interior. When you translate that geometry back to real time, you get an expanding sphere. Its wall is a thin region where the field transitions between minima. Inside, the energy density is lower, so the pressure difference drives expansion. The bubble wall accelerates and quickly approaches the speed of light relative to the surrounding false vacuum. Where does entropy enter your entropy blast? The change in vacuum energy affects the thermodynamic state of whatever degrees of freedom are coupled to the field. If the true vacuum has different particle masses or interaction strengths, the degrees of freedom reorganize. The expansion converts stored vacuum energy into excitations, radiation, particles, and gradients. In many models, the bubble's interior heats up, and that reheating can correspond to a large increase in entropy within the bubble. Entropy isn't uniform. It concentrates in the bubble's vacant wall as energy is released and thermalized. So the term entropy blast captures that the transition isn't merely a static swap of energy states. It is an out-of-equilibrium event that scrambles microstates and produces disorder and heat in the region that becomes causally connected to the bubble. Historically, the shift from thermal transitions to quantum tunneling in field theory was pivotal. Once theorists treated false vacuum decay as a dynamical tunneling process with a calculable nucleation rate, the rate became an integral quantity, roughly exponentially suppressed by the action of the bounce. That made the phenomenon simultaneously plausible and constrained. If the action is large, bubbles are so rare that metastability can persist longer than the age of the universe. If not, vacuum decay would have already happened. This is why the framework is testable indirectly. By comparing predicted lifetimes to cosmic timescales, particle physicists can rule out or bound regions of parameter space. And that brings us to the broader implications. If false vacuum decay is real, the universe we observe is not guaranteed to be the ultimate ground state. It's a metastable snapshot that reframes inflationary models too. In many scenarios, inflation corresponds to being stuck in a high-energy vacuum-like phase. The end of inflation then resembles vacuum decay through bubble nucleation, turning vacuum energy into a hot, expanding cosmos. Even outside inflation, vacuum structure determines the stability of the Higgs sector and other fields. For example, if the effective potential of the Higgs field has a deeper minimum, we can ask whether quantum tunneling would destabilize our vacuum over time.
Constraints on that decay rate feed into what new physics might exist at high energy scales. There's also a conceptual consequence. Entropy. Blass suggests that reality could be reshaped locally and then globally in a causal sense. The bubble wall is a boundary beyond which the field state and the effective laws governing excitations differ. Observers outside the bubble may never see what happens inside. They only know that the region they can influence becomes part of a different phase.
In other words, vacuum decay offers a mechanism for a sharp, causally propagating change in the universe's state, paired with dramatic reduction of entropy that records the transformation in the second law's language. So what do we take away? We started with the misconception that empty space is featureless. Nothing. We replaced it with a structured quantum field environment where the vacuum can be a metastable trap. Then we followed the tunneling logic. A false vacuum can nucleate a bubble of true vacuum when quantum fluctuations create a critical configuration, described by a cephalhedical bounce. Global expands because of the vacuum energy difference. Its wall races outward, and the released energy can heat the interior and generate a burst of entropy as degrees of freedom reorganize and thermalize. The final picture is not a slow cosmic fade, but a rare, probabilistic transition whose rate depends on the shape of the potential. If our universe is metastable, the question, what if the vacuum decays, is not science fiction, it's a calculation, and every calculation is a timer, hidden inside the equations that describe nothing. If you want more cosmic suspense with real physics, subscribe.